You all got a similar problem to this in your prep for section 4. We did a problem like this in class with ibuprofen and then with coffee yesterday. So give it a shot, see what you can get with this version right here. Here we're taking the half-life of caffeine to be 6.5 hours. Starting with 100 milligrams and a cup of coffee. I would recommend starting off by building a table for this. Okay, so start by building a table. So either whip it out on a piece of paper or on a spreadsheet. So this is a lot like that second table we made for the carbon-14 yesterday. How should I start off my table?
Hour 1, 2, 3.
Not hour 1, which should we start with first? Yeah, so I'm going to start with a 0 hour so you can get the initial amount. So I'm going to go hours and then 100 milligrams. And sometimes we just go 1, 2, 3, what? Do we have enough information at the moment to jump straight to 1, 2, 3, or is there an easier time to plug in next?
Yeah, it's half-life, right?
Yeah, plug in the half-life. So we know that in 6.5 hours, that we're going to have half of what we started with. So 6.5 hours later, how much caffeine are we going to have? 50 milligrams. Can we make another jump on the table, get another pair of points? So another half-life later will be what time? What's that?
Oh.
Well, we're going to have 25, but at what time? 13, yeah. So 6 and 6 is 12, half and a half is another 1. So 13 hours from when we started, which is, again, a jump. Every 6.5 hours, we are going to drop by 50%. So we're going to end up with half of what we had before. We can keep doing that over and over again. So if the half-life is 1, this would be a lot more straightforward. So as far as time goes, what are we grouping by? What's our important time here?
6.5.
6.5, yeah, so we're looking for groups of 6.5 hours. That makes it easy. Every time we find a group of 6.5 hours, we get to cut it in half. Okay. So what mathematical operation looks for groups of something? Like how many groups of 2 are in 24? What am I doing there? What's that? So I can hear it. Yeah, but how'd you calculate that? You did multiplication? Where'd you get the 12 from? I started with 24 and 2.
Oh, division.
Division, yeah. When we're looking for groups of something, and here we're looking for groups of 6.5 hours, we do division to get there. So here's how the order of operation works. Like Jenna was hoping for 1 hour or 2 hours, but maybe it's more than that. Right? Maybe we're looking for 24 hours later. So the first thing I want to do is when someone gives me the time, I want to see how many half-lives are in there. And the reason I want to do that is every time I have a half-life, I get to cut it in half. So that's the easy part. So this right here is my power. So this is like the ibuprofen problem we did the other day. So if that's the power, then I have to have a base. So every time I find a half-life, what am I going to do? Every time I find a group of 6.5 hours, I'm just going to cut it in half, right? 0.5. So I'm just going to cut it in half. So I multiply by 0.5 every time I find a group of 6.5 hours, starting with 100. Let's clean that up. So this is the formula that we're looking for to calculate the caffeine. I'm going to throw this in a spreadsheet in a minute and see what the spreadsheet thinks of it. Let's see. New spreadsheet. All right, so I'm just going to make a note. So we're talking about caffeine. And then we have the half-life, 6.5. This is number 5 in the 6, no, number 5 in 4 force prep. So 6.5, oops, hours. What else? I do somewhere here. There's one for you. Starting at 100 milligrams. So I'm just going to plug in what I started with on the board. So the easiest thing to do with a half-life problem is just jump by the half-life. So in my spreadsheet, I'm going to start with 0 always. And then every 6.5 hours, I can even go one more. Let's see, what would that be? 6 and 3 is 9, it's 19.5. I'm going to keep cutting in half. So I'm just going to take the number above and multiply by 0.5. And I can just fill that down. So remember, we can have the computer graph these. So I could make a chart here. And I want to see it as points. I better zoom out just a little. And I don't think I'm going to worry about customizing at the moment, except maybe to get rid of the legend. All right, so the points are dropping down. Do they drop down in a straight line? No, they're definitely curving because this is an exponential. It's going to have that hockey stick kind of shape, that curve to it. And remember, we can ask the computer to find an equation through these points. So I'm just going to do that for fun and compare it to the equation we found. So, and I'll give you guys some time to go to the lab and play with this if you don't have a computer. So let's see, I want to edit the chart and customize the series to show me a trend line. Now it wants to put a straight line. What should I pick instead? Yeah, this is an exponential. Now, when computers do exponential, they usually use a number called E. And I haven't talked about E yet, but we did, thanks to Daisy, talk about, remember the natural logarithm yesterday? E is related to the natural logarithm. So let's see, what else do I want to do? I want to label it to show me the equation. All right, so let's get out of there. So it says 100 times E to the power negative 0.107. So I'm going to screenshot that and see if I can make sense of that compared to what we found. And so you guys are going to help me check some things here. So this is the computer's version of the formula.
So on that, is your power T over 6.5?
Yeah, T over 6.5 is the whole power. So
Okay.
it'd probably be a good idea to put that whole thing in parentheses, that power. Yeah, so I'll try typing that into the spreadsheet in just a minute, and I want to compare it to what the computer did. Let's see, what is that doing right there? Oh, X is the variable it's using instead of T. Okay. So interpretation of what the computer wrote right here. Let's see, I'll put that in red. So it's definitely starting off with 100 like we are. And then E is kind of like pi. Pi is 3.14 and it keeps going on and on and on. E is like that, it's 2.7 something. So some calculators have an E button. Let's see if the Google calculator does. It's not giving me a calculator. What if I go E times 1? There's my calculator. So Google says E, like, it's a magic number like pi, is 2.71828. So if I went out to 3 decimal places, I call it 2.718. So my base is about, I'll put a wavy equal sign because I'm going to round E, 2.718. And then they're saying use the power negative 0.107. And in this, they're using X on the computer. We're going to use T for time. So I've got 2 different versions of this formula. So write down each of these, and then we'll test them out on a calculator, see how they perform. So backing up a page here, 6.5 hours further down here, that's going to put me at 19.5, and half of 25 would be 1250, or 12.5 milligrams. So just after 9.5 is 20. So it's going to be a little lower than 12.5 because we're dropping, right? So I'm going to say in 20 hours, the answer is going to be about 12 milligrams. Maybe a little tiny bit more than that. Does that seem reasonable based on the table? Okay, so what we're going to do is we're going to calculate for 20 based on our formula. So we've got 2 versions of the formula we're going to test out. So I'm going to let T equal 20 hours. And the first formula said to get the amount of caffeine, take 100 times 0.5 raised to the power the amount of time that's gone by, and then how many half-lives are in there. So the amount of time over 6.5. So try typing that into a calculator and see what you get. So I'm going to try typing that into my Google calculator. So 100 times 0.5 raised to the power, and I have to use parentheses, 20 over 6.5. And I'm hoping to see about 12 is what my table predicts. And 11.85. Okay, that's about 12. Anyone else getting that number? Anyone not getting that number? Better answer. Everybody needs to be good with their calculator. You okay, Jenna? Okay, Cole, Aaron, good? Okay, Elena, you good? Okay, so then we'll try the other version. So that seems to work out. It's about 11.85. That seems reasonable. The spreadsheet version of the formula said to calculate the caffeine, take 100 times E, the number, which is a lot like pi. I'm going to say E is approximately 2.718 raised to the power negative 0.107 times the time, which will be 20. So that would be the spreadsheet's version of the formula. They look different. Let's see if they match up. 2.718 is about E raised to the power parentheses negative 0.107 times 20 hours later. And that gives me, okay, so that's a little lower. How come you think that didn't work out as well? It's close though, right? It's in the ballpark. Not way off. Any guesses as to why it's a little off there compared to my first formula? Not quite. So the negative sign is important. When E is the base, a negative sign means it's dropping, and a positive power means it's rising. So it's negative, this is dropping, that's good. But the computer had to calculate the 107, and so it had to round that number when it did the calculation. So I have rounding error from that power right there. Do I have any other rounding error here? Did I use exactly E, or did I put an approximation of E? Yeah, I rounded E, kind of like we round pi to be 3.14. I rounded E, so I have 2 places where I have rounding error, which leads to a little rounding error in my answer. Whereas the formula we came up with first, doubling time is 6.5 hours. That's pretty straightforward, and it cuts it in half. So there's very little rounding error until the very end on this one. Okay, so this one is a little more accurate, but when you have a computer that can calculate a formula for you, that's a pretty powerful tool. And that's just, there's a little rounding error there is not a big deal. Check out your calculator. Does your calculator have an E button? So on the Google calculator, there is an E. So instead of typing 2.718, I can just put E in there, and I should get a little bit better answer. Oh, not much. Yeah, it'll probably be the EX. Let me say. Yeah, that's it. Yeah, so you would hit second. So just try that. So hit second in that key, and then give it the first power, just 1. And then hit enter, and then you get that 2.718. Yeah. On a spreadsheet, there's an E somewhere. Let's see, how do we get that on a spreadsheet? For those of you who are using spreadsheets, E, what if I just type E? On a spreadsheet, it's called EXP. And it's called Euler's number, and here it says it's about 2.718, which is what I was calling it. So what I would do is type EXP, and then it wants what power am I raising it to? So if I give it the first power, it'll tell me about what E is. Okay. So we can get E on a spreadsheet too. All right. Yeah, yours does have it somewhere. Let's see. So I'll quit out of that. It is right, let's see, right there. So I hit second ln to get it. So try second ln, and then give it the first power to see what E looks like. Yeah. Elena, do you have E on yours?
Yeah.
Are you on a spreadsheet or a computer calculator? Okay. All right, so just a couple notes about E, and then we'll move on to the worksheet. So E is sometimes called Euler's number. Euler was a math guy from a long time ago. It looks like Euler, but it's pronounced Euler. And it's approximately 2.718. Let's go 1828, say. And it keeps going without a pattern, kind of like pi does, a lot like pi. If you have a log and you use E as the base, that's supposed to be an X, that's what we call the natural log. So Daisy brought up natural log. It's a key on the calculator. Natural log means log base E. E is about 2.7-ish, right? It's a popular log because E comes up in a lot of different places. E pops up in the math of finance. E pops up in biology. E pops up in physics. So kind of like pi pops up in different places. In reality, E pops up in different places. It just doesn't get as much attention as pi, because pi is pretty obvious. It comes from circles. E comes from these more obscure places. But it's a pretty important number in math. So important, it got its own special name here. The natural logarithm is related to it. Okay. So it's just kind of something to get used to. It's not a huge deal, but it can be helpful. All right. So that caffeine problem is a tough one. We're going to go over ones like it a couple of different times. So that's a good start on that. Hopefully enough for you guys to finish that homework problem. Let's take a look at the worksheet for today. So in class yesterday, we played around with the first few problems using this formula they give for the problem situation, first paragraph, to calculate what's going on here. What was the trick to using this formula here about T? Anybody remember? Is T just the time, the number of years, or is it something else? Yeah, it's every 1,000 years. So like here, where it says 6,000, I would plug in T equals 6, because T measures thousands of years. So that was the trick in using that formula. And then here, the half-life of carbon-14 is 5,730 years. So just like with the caffeine, it made sense to jump every 6.5 hours. On this table, we're jumping every 5,730 years. So there's 1 jump, 2 jumps, 3 jumps, and 4 jumps. So what'll happen is the amount will be cut in half. the trick on this one right here, how much are we starting with? Are we given an amount? No, we're just talking about the fraction of it. So at first, I'm going to have 100%, which as a fraction is 1. 5,730 years later, how much am I going to have? If that's the half-life. Yep, half, 0.5. And another 5,000, so I'm jumping here by 5,730 years each time. So what's half of a half? Yeah, so we just keep cutting this in half, and that's giving us the fraction remaining in this table right here. So kind of like the caffeine, if I wanted to make a formula based on the half-life, what's the important number of years here for carbon-14? Not 1,000. Yeah, 5,730 is the magic number, because every time 5,730 years goes by, whatever carbon-14 was in the thing is now cut in half. We have half of what it used to. So that's the magic number. What was the magic number with caffeine? No? 6.5 hours. Yeah, every 6.5 hours it got cut in half. So that was the magic number. So in the half-life for caffeine, we were looking for groups of 6.5. Here we're looking for groups of 5,000. So here's the way I would build the formula. I get to cut the amount in half, 0.5, every time I get a group of 5,730 hours. How do we find groups of a number? What operation? Division. Division. Yeah, so I want to take however many years have gone by, and I want to say, okay, how many groups of 5,730 are in there? If I find a group, I get to cut it in half. And then you're going to have some kind of starting amount. So this is a formula based on the half-life. So we're going to play around with that formula and see how it relates to the formula on page 1. So just let's let let's see, what do I want to do? Let's let T be 1 just for fun. So then I'm going to have 0.5 raised to the power 1 over 5,730. So type that into your calculator, see what you got. So I got to use parentheses to do that. So I've got 0.5 raised to the power parentheses, because I got to do division in the power, 1 over 5,730. Ooh, doesn't like that. Maybe we need to try a bigger number besides 1. Let's try 1,000 years instead of 1 year. Okay, does that number look familiar? 0.886, what would I round to get 4 decimal places? 8861, not looking familiar? So that's what they gave me on page 1. They said if you go by 1,000 years, you can use the base 0.8861. Okay, so I'm just making the connection that the half-life version of the formula matches what they were talking about up there. All right, so I'm going to leave you guys to play around. I'm going to shut up for a little bit. You need to answer number 4, check with your neighbor, and then start taking a look at the idea of planetary distance and how we can use logs and exponents to talk about that on the next page. So get that started for 4 and then jump over to the planetary stuff and questions 5 and 6, and then we'll regroup after you guys have had a chance to talk about it. So start writing and find someone to talk to. Daisy and Emily, maybe you guys can chat with each other on the Google Chat. But feel free to ask me questions too. How's it going, Colt?
Alright.
You're stuck? Which one? So you have two formulas you can use to do it. You can use the formula they give on page 1,
I tried using that one.
or the one we just made. Okay, where'd you write down? You just type it in. This is one I need to write down.
What I use to like multiply by the 0.5.
So since we're just going by percentages here,
So I
nothing. So we would just set the formula equal to 20% as 0.2.
Okay.
So for that one right there, let's see, let's get a new page. So the formula we just came up with was 0.5 raised to the t over 5,730. And then we want to know when is that going to be equal to 20%, 0.2. So then we can use logs to try and solve that. So give that a try, see what you get. So like we were playing with logs yesterday.
What? That's what I was confused about. Is what do I do with the 20%?
So you can't just plug this into a spreadsheet. You got to write it on paper and try and solve it. We had two techniques. One was to rewrite it as a logarithm statement. The other was to use by taking the log of both sides. Those are the choices on this one. I missed that fun yesterday.
Yeah. Would have been more fun than
Yeah. I was over my cold yesterday, last night.
I don't get how X reverse.
I'll reverse that. No, that doesn't do it. That's just a guess. We're trying to confirm that guess. So erase that, and you want to just set this equal to 0.2. All right, Elena, do you have any luck on this one?
I don't know.
What did you try?
I tried to set the first formula from
The book's version?
the what?
With this one here, or the one the worksheet had?
The one the worksheet.
Okay, so that was the 0.866, what was it? 8861, thank you. To the power t, and set that equal to 0.2?
Yeah.
Okay, so what did you do from there?
And then I logged both sides.
Okay, so I'm going to take log of both sides. Good, that'll work. And then what?
I like, I don't know how to explain it.
Did you pull the t out next?
Yeah. That's,
Okay, yeah. So then if there's a power inside of a log, we can pull the power out. So that becomes t times the log
Yeah.
of 0.8861. And that's equal to the log of 0.2.
And then I
Divide that over, yeah. So we'll divide by the log. And so that right there is the answer I want to plug into my calculator. So t is supposed to be equal to that. So let's plug that in, see what we get. So I've got the log of 0.861, close that one, divide by the log of 0.2. And my calculator says 0.07. That's what this formula claims t is.
Wouldn't you divide it the other way around though? Like the log of 0.2 divided by the log of 0.8861?
No, because I'm trying to get t alone, so I have to break this multiplication right there. So then the point on this side is that this is basically a number divided by itself,
Yeah.
which is 1. Oh, did I
Yeah.
type it in backwards on the
Yeah.
computer? Oops, I typed it in upside down. Yeah, thank you. All right, flip that sucker. Good call. All right, there we go. 13.3. That's more like it. All right, what is t measuring with the equation on the first page of the worksheet? Thousands of years. So what this really means is 13,000. So 13,300 years roughly. And I saw a bunch of people guess at around 12,000 years. That's the ballpark in the thousands. That's all right. So just for fun, I'll redo that with the other version of the formula, see if it matches. So special note here, we had to remind ourselves that t was thousands of years. All right, I'll give you a minute on that, and then we'll try the other formula, see if we can get a match for that. All right, ready to try the other version? So the other version put us right here. So we have two options. We could take the log of both sides, or we could rewrite it as a logarithm. Who wants to call it? Colt? Which one? Jenna? Rewrite it as a logarithm? Okay, so to rewrite it as a logarithm, the first thing I do is write down the power. The power here is t over 5,730. And a power is always equal to a logarithm. What base should the logarithm have? 0.5, same base as up there, so I write that down here like that. And then parentheses, the target was the 0.2. So that's rewriting it as a logarithm. What's that? Now mine is different from yours. You have the older version, which asks about 14%. Mine's asking about 20%. So you can just switch yours to a 20%, so for 14. That number's not too critical, but since everybody else has the other one, we'll do this. So how do I rewrite log base 0.5? It's going to become the log of 2 divided by the log of 0.5. So I'm almost done. How am I going to fix this to get t alone? Yeah, multiply the 5,730 to the other side. So then finally, I'm going to get t should be whatever that log of 0.2 over the log of 0.5 is. And then I want to times that by 5,730. So let's try plugging that into a calculator and seeing what it gives us. So log of 0.2 over log of, and you could use the common log, the natural log, ln instead if you want, 0.5 times 5,730, And Google tells me that it's 13,304 years, 305 years. So pretty much the same number we got before. Two different approaches. You can pick whichever one you like. Oops. All right, ready to move on to planetary distances? Almost. Screenshot this. Oops. And the graph. So there's a problem when we try to look at distances like these. Mercury, Venus, Earth, Mars, they're not too far apart. But then all of a sudden when we start to look at Jupiter, Saturn, Uranus, and Neptune, it's hard to, Mercury, Venus, and Mars get all clumped together down there. Are they really close together? Not really, they're pretty damn far apart, right? We've gone to the moon, but humans haven't made it to Mars yet. So they're not as close as they seem. So a lot of times when we're talking about really big numbers like this that are hard to fit all together on the same scale, what we do instead is we look at about the power of 10 that they represent. So that's called a logarithmic scale. So if you look at the next graph down here, instead of scaling where each of these marks measures 250 million miles, what we do instead is we just think about powers of 10. So here's 10 to the 1.5, here's 10 to the 2. So I'm not scaling by the actual number, I'm scaling by their power of 10. So notice 10 squared, 10 to the third, and 10 to the fourth, they're the same distance apart in pairs. The distance from 10 squared to 10 to the third is the same distance as 10 to the third to 10 to the fourth. Okay. So just think about that for a minute. What is 10 cubed? 1,000, right? So I'm just going to steal this. Oops, wrong button. Into my worksheet. So 10 cubed is 1,000. 10 to the fourth is then 10,000 because it's another 10. 10 squared is 100. Are 100 and 1,000 really as close together as 1,000 and 10,000? The answer is no, they're not. We're just rescaling here. This kind of scale here where we scale by powers, that's called a logarithmic scale. And what it does is it allows us to see certain figures on the same number line that we couldn't otherwise. We couldn't compare them otherwise, is what it allows us to do. And it's a powerful idea. It comes up in a lot of different places. So anybody know what decibels are? Sound familiar? Lena? No? Yes? Where'd you hear it before? Sound, yeah. Decibels is a measure of loudness, okay? So decibels, loudness of sound. Anyone ever hear of the Richter scale? Okay, Richter scale measures the intensity of an earthquake. Okay, anybody ever heard of pH? So pH is a measure of, I think it's sodium ions, so it tells you whether something's very acid or very basic. Okay. All of these scales, decibels, Richter scale, pH scale, they're all logarithmic scales. Because when we talk about the percent of sodium ions, we can have a really small percentage or we can have a really high percentage, and we can't see them on the same number line together is the problem. And so that's what we're getting used to in the rest of this activity here, using a logarithmic scale so numbers can be more comparable. All right, so we're going to break here. If you haven't finished the prep for 4.4, please get it done. Work on this worksheet on your own tonight, and then we'll work some more on it as a group tomorrow.